This video lecture is meant to cover Chapter 8, Section 4, which explores the idea that covalent bonds can be classified as either polar or nonpolar. And to classify those bonds in that regard, we have to learn a little something about electronegativity, which is a property of atoms that is described by a number, and you can see those numbers here in this chart. Electronegativity can be defined as the ability of an atom to attract a pair of shared electrons. Well, we can see here in this diagram, we can see that there is a shared pair of electrons. Well, first of all, this is an atom on the left, the big blue one, and this orange one is another atom on the right. There's definitely a size difference, and that's going to come into play in our explanation of why electronegativity, why it does what it does. But if this is an electron here and this is an electron here, it is this pair of electrons that is the covalent bond, and it is those two electrons that are being shared between the atom on the left and the atom on the right. Well, it turns out that this shared pair of electrons is not shared equally by these two atoms. Sometimes atoms can share them equally, but many times the two atoms are different enough that the sharing power is different from the two atoms. Let's take a further look at these numbers that you see on the chart down below. You'll see numbers here described from 0.0 would be the low end all the way up to 4.0, where 4.0 is considered to be the strongest. It's the high end of the scale, and if an atom has a 4.0 electronegativity, it can attract a pair of electrons very, very, very well. Well, if you take a look here, we see that fluorine is the most electronegative element on this chart. And in fact, it is the most electronegative element on the periodic table. And if you remember back to our unit on atomic radius, fluorine was one of the very smallest atoms on the periodic table. And so you can see here that as you go from left to right, electronegativity values tend to get larger. And so there is a trend. Smaller atoms tend to have higher electronegativity values. Now, to explain why, let's go back up to this diagram in the upper left corner. If we have this atom, the atom on the right, which is smaller, the nucleus, this yellow center, is positively charged. And this positive nucleus is attracting this shared pair of electrons with a certain strength. The atom on the left also has a positive nucleus, and that positive nucleus is also attracting this shared pair of electrons because, of course, opposites attract. The nucleus is positive, the electrons are negative. But the difference here is that because the atom on the right is much smaller, the distance from the negative electrons to the positive nucleus is much smaller, and so therefore smaller atoms tend to be able to hold on to that shared pair of electrons more strongly than atoms that are larger, just by the nature of the fact that those shared pair of electrons are further away from the positive nucleus. So, bottom line, smaller atoms tend to have stronger electronegativities because the distance from their positive nucleus to the negative shared pair of electrons is shorter, and therefore that atom can hold on to those electrons more strongly. Now, if you notice here, noble gases don't have electronegativity values. Why is that? Well, it turns out noble gases don't actually participate in covalent bonding. They can if they are forced to, but typically they do not form covalent bonds. So if they're not forming covalent bonds, they're not sharing electrons. And if they're not sharing electrons, you can't describe an atom to have an ability to attract a pair of shared electrons because the sharing is just not happening. Now, we said that the point of this lecture was to classify covalent bonds as either polar or nonpolar. So here's where we're going to start to define what those two distinctions are. A polar covalent bond. Now think polar as in North Pole, South Pole, opposite ends of the planet. All right, so a polar covalent bond is when you have two shared electrons that are shared unequally between two atoms. So the example you just saw, where you had a very large atom covalently bonded to a very small atom, those electrons in that covalent bond will be shared unequally, and therefore be considered to have a polar covalent bond. So those two shared electrons are shared unequally because one atom has a higher electronegativity than the other. A nonpolar covalent bond is when two electrons are shared equally between two atoms. And the only way that they can be shared equally is if the two atoms have very similar or even the same electronegativity values. So if two atoms participating in a covalent bond share equally well, then we say that that bond is classified as a nonpolar covalent bond. Well, so to actually have some examples where you'll be given two atoms participating in a covalent bond, and you'll have to decide, is that bond type a nonpolar covalent bond? Is it a polar covalent bond, or is it ionic? So let's see how we do that with this electronegativity business. What I will have you do is you will determine the electronegativity difference, which I am going to abbreviate as END, electronegativity difference, between the elements that are participating in the bond. If the difference is very small, and by small I'm referring to a difference of 0 or a difference as large as 0.4. If that's the case, if there's a small difference, we will say that the bond is nonpolar. And if it's nonpolar, that's because the electrons are being shared equally. If there's a medium difference, let's say the difference between the two electronegativities are somewhere between 0.4 and 2.0, then that means that the electrons will be shared unequally and the bond will be considered to be polar. Now, if the difference is large enough so that the difference in electronegativities is greater than 2.0, then what that means is that one atom is so strong it actually won't share electrons at all. It'll actually steal electrons from the other atom. And in this case, it won't be a covalent bond at all. It will be an ionic bond. And we say that the electrons are transferred. They're not shared. So let's do a couple of practice problems. Finding the END, the electronegativity difference. Here's a chart here for your reference. And what we have here is the first example is potassium and fluorine. If we find potassium on the periodic table, we see that its electronegativity is 0.8. Fluorine on the periodic table is a 4.0. So if we were to try to bond potassium and fluorine, the electronegativity difference is 2.2, and since this is a very large electronegativity difference, it turns out that the fluorine will actually steal the electrons from the potassium, and the bond will be an ionic bond. Example number 2, sulfur on the periodic table has an electronegativity of 2.5. Oxygen on the periodic table is a 3.5. So the electronegativity difference is 1.0, which classifies this bond between sulfur and oxygen to have a medium difference, and we would say that the bond is covalent, but a polar covalent bond, so that the electrons are not being shared equally. In fact, the oxygen will want those electrons a little bit more than the sulfur. Nitrogen has an electronegativity of 3.0. Oxygen has an electronegativity, as we saw in a previous problem, of 3.5. The difference here is 0.5, which classifies this bond as a polar covalent bond. So in example 2, we had a a difference of 1.0, and here we have a difference of 0.5 in example 3. So there's sort of a spectrum of polarity of bonds. It's not just one. Even within the polar bonds, there's a whole range of polarity. Example number 4, chlorine. If you wanted to bond two chlorine atoms together, well, the electronegativity, since it's two atoms that are identical, the electronegativities will be identical, which means that the difference will be 0. So here, the two chlorines will share the electrons in the covalent bond equally, and we would say that that bond is a nonpolar covalent bond. Example number 5, bonding carbon and hydrogen. Carbon has an electronegativity of 2.5. Hydrogen has an electronegativity of 2.1. The difference here is 0.4. Now, when you find an electronegativity difference of 0.4, we will classify that on the lower end, and we'll say that that bond is a nonpolar covalent type of bond. We say that essentially the electronegativities are identical, and we'll classify those shared electrons as being shared equally. Our last example is the bond between hydrogen at 2.1 and oxygen at 3.5. The difference here is 1.7, and that classifies this type of a bond as a polar covalent bond. So this bond between oxygen and hydrogen is even more polar than the bond between sulfur and oxygen, which is more polar than the bond between nitrogen and oxygen. So this electronegativity difference just shows you that there is a spectrum of electronegativity differences, and the larger the difference gets, the more polar the bond gets, until at some point the sharing is so unequal that the bond actually is classified as an ionic bond. Here we see, we're going to talk about this as in a larger scale, where we're going to talk about molecules containing polar covalent bonds. Here we saw that the electronegativity difference between oxygen and hydrogen was a polar bond, and if you recall, oxygen was more electronegative than the hydrogen. So the electrons are being pulled towards the hydrogen. Sometimes you'll see chemistry textbooks will show the direction that the electrons are being pulled in each of the bonds with a funny little arrow with a line through it, right? And so what this is showing you is that this is an arrow. It's actually called a dipole moment, kind of a funny little word. But the electrons are being kind of pulled towards the oxygen, so much so that there's a slight charge on the oxygen end, and that is often shown as a Greek letter S. This is a sigma, and it'll have a sigma minus charge. That's to show not a full -1 as it would be in an ionic compound. It's just a partial negative charge that's sort of built up on this end of the molecule. Now, conversely, if the charge builds up on the oxygen end of the molecule, that means the hydrogen ends of the molecule end up being slightly positive. Now, if we do the same thing over here on the second water molecule, showing that the direction of the electrons are being pulled towards the oxygen, we'll see here that this oxygen has a slight negative charge, and these hydrogens have a slight positive charge. And so what you can see here is that there will be an attractive force between these two water molecules, right? And so this is what is referred to as dipole attractions, where the partial charge on one molecule is attracted to the opposite partial charge on another molecule. So the water molecules themselves being the dipoles, and the attractions are between the molecules. Now in this case, this is an example of a dipole attraction that's a fairly strong dipole attraction, because water is a strongly polar molecule. And in that case, when you have molecules that are strongly polar, the dipole attractions have a special name called hydrogen bonds. And so you can see here when water turns into a solid, water actually arranges itself into this hexagonal shape, which is why ice is less dense than liquid water, because the solid form has all these empty pockets of space in between them, which decreases the density of the ice and compared to its liquid state. But these hydrogen bonds, you can kind of see these here, designated by these dotted lines. That's the hydrogen bond. You also will find hydrogen bonds holding together the double-stranded DNA. If you recall from biology, when DNA had to unzip for replication purposes, it unzips when the hydrogen bonds are broken by the certain enzymes that do that. Now, it is these intermolecular attractions that allow water to exist readily in the liquid state. Because of these attractions, it holds water molecules together, and their desired natural state at room temperature is to be in a liquid form as opposed to a gas form. Nonpolar molecules don't have a strong buildup of charges on one end of the molecule compared to the other. And so nonpolar molecules often tend to be in the gas form because there's just not a whole lot of intermolecular attraction holding them together. This is a case of acetylene, which is the gas that is used in welders' torches, and it burns very brightly and very hot. But we can see here that this carbon to hydrogen bond had an electronegativity difference of 0.4. This bond would have an electronegativity difference of 0 because carbon atoms are the same, so they would have an equal pull on these electrons. And then this carbon would pull on these hydrogen atom electrons right here weakly. This is the bond that has that difference of 0.4. So it is there is a slight difference, but it's not enough of a difference to classify this as a polar bond. So basically, the electrons are just distributed evenly around this molecule, and of course this is an identical molecule. So there's no partial charge like what we saw up here with the water molecule. So any attractive force between these, it just doesn't really exist. Now, that being said, there are sometimes temporary attractions that build up. It's kind of like a randomization. Sometimes the electrons that are holding all these atoms together, just for a brief moment in time, the electrons might pile up towards one end of the molecule. And in that brief moment, this molecule as a whole would have a temporary polar charge to it. One end would be slightly negative, the other end would be slightly positive. But it lasts briefly, and it really is not a very strong force at all. But it does exist, and it is called a dispersion force. And it is created by just those temporary dipole moments, just essentially from a randomization, a random piling up of electrons on one end of the molecule. But it's not strong, and it does not last very long. Now, we can use this information to help us figure out what things will dissolve in other things. This is really useful when in the household when you're trying to clean up a mess. Grease, you can't clean up a greasy mess with water. You can, however, pick up a greasy mess with a cleaning solution that has the right properties. So that's where this kind of chemistry is actually useful in your day-to-day life. And this is this, for example, is how you would use chemistry in your real life. So you're going to see a video here which is going to show you 3 different solvents. There's going to be something called ethyl acetate, water, and chloroform, and they'll be put into that order. You'll actually see 3 different layers because chloroform is a nonpolar liquid, water is polar, and ethyl acetate is nonpolar. So the nonpolar chloroform will not mix with the water, and the water is less dense than the chloroform, so the water will float on top of the chloroform. The ethyl acetate is less dense than water, and since the ethyl acetate is nonpolar, it will just sit on top of the water. So you'll see 3 liquids in 3 different layers. Now they're going to add 2 different solutes. They're going to add iodine, which is the brownish purplish substance, and they're going separately they're going to add copper-2 sulfate, which is blue. And what you will see here, well, let's go ahead and play it and see what you can see. So if we go back and take a look at a still shot from the video, we can see that the iodine, which is brown in ethyl acetate and purple in the chloroform, we can see that the iodine dissolved in the nonpolar solvents. The copper-2 sulfate, which is a known ionic substance, dissolves in the polar solvent, but not in the nonpolar solvents. So it turns out that depending on the properties of the substance you want to dissolve, the solute, depending on these properties, that'll determine whether or not it will dissolve in either a polar solvent or a nonpolar solvent. So it turns out that iodine is nonpolar. So that's sort of interesting that the nonpolar solute dissolves only in nonpolar solvents, but the ionic solute, copper-2 sulfate, the blue, dissolved in the polar solvents. There's a saying, this like dissolves like. Solvents that are nonpolar will dissolve nonpolar molecules only. Polar solvents will dissolve ionic compounds, which is what we saw here with the copper-2 sulfate. And polar solvents will also dissolve polar molecules, which was not demonstrated in this video. But the idea is that like dissolves like. Polar solvents will dissolve ionic compounds and polar molecules because polar molecules and ionic compounds have charged particles associated with them. Nonpolar solvents will only dissolve nonpolar molecules. So this concludes the video lecture from Chapter 8, Section 4. See you in the classroom.